Flow tutorial question number 24. Air flows from a 25 degrees Celsius reservoir to the atmosphere through a nozzle with a 50 millimeters diameter throat and a 100 millimeters diameter exit. What reservoir pressure will just result in Mach 1 at the throat? Also calculate the mass flux. Maintaining this reservoir pressure, reduce the throat diameter to 40 millimeters and determine the resulting mass flux. So from this question, I hope you could imagine this device. We have a reservoir here with a certain pressure, and then we connect this reservoir with a convergent divergent nozzle. And the smallest cross-section area here is known as throat. And then we hope a pressure here will create flow, subsonic flow here, and then increase to the Mach number 1 at the throat, and then will accelerate with certain Mach number exceeding 1 at the outlet. So we could say that pressure at reservoir here is the stagnation pressure, because we have pressure inside the reservoir but we don't have any velocity here, so it is suitable as stagnation condition. So Mach number here is 0, velocity is 0, but in reservoir it has a certain value of pressure. So we could say that pressure at reservoir here is P0, which stagnation pressure. At throat here, so we could say it is a critical pressure, PT. T is for throat, because Mach number at throat usually is equal to 1. And then this is the outlet. So at least at the outlet, we could say that the atmospheric here is the final pressure that occur at outlet. So we could assume that P2 will P2 is equal to the atmospheric pressure. And in compressible flow, it is important for us to calculate all in absolute pressure. So means that the atmospheric pressure will be assumed as 101 kilopascal. First, we calculate the ratio between the exit cross-section diameter, cross-section area, and the critical area. I hope you still remember that for critical area where Mach number is equal to 1, we show the parameter with asterisk here. So the A star here is referred to the cross-section area at the throat. So the diameter was given in the question for diameter for exit and diameter for throat. So we could calculate the area ratio, A2 over A star, and we have a pi d squared over 4 here. We substitute the value of diameter for exit and for the throat, and we could get is equal to 4. And then if we refer back to the question here and our diagram here, the question didn't mention any terms about shock wave. So means that there are no shock wave occur at this system, and we could calculate all these 3 points by using the isentropic flow. So we refer to isentropic flow table here. So we found that for ratio 4, so we see at column for A over A star here, and A here is referred to the exit in this question. So we refer to the exit and throat A over A star here. So we found that the ratio of 4 is between 3.6 and 4.1. So mean we must calculate it by using the interpolation method. So we could say that the Mach number here, because we take A here is A for point number 2, so Mach number here will become Mach number at point number 2. So we do the interpolation calculation. We could say that if the ratio is 4, means some certain value here, the Mach number is equal to 0.47. So please make sure that you could calculate by interpolation method. So we could, from this table, we could say that we could get M2 here, Mach number at exit is 0.147. We also could calculate the ratio of P2 over P0. P2 mean pressure at exit over P0, P stagnation. So we don't have exact number here. Again, we must do the interpolation calculation here. So we could get 0.985. From here, we could calculate the pressure at stagnation, mean the pressure at reservoir, by having P2 divided by 0.985, and as I described previously, at exit the pressure will equal to the atmospheric pressure, so we use 101 kilopascal here. We solve this equation, we could say that stagnation pressure, which is equal to the pressure in the reservoir, is equal to 102.54 kilopascal absolute. Then we need to calculate the mass flux at throat here. And the mass flux means the mass flow rate. And the equation for mass flow rate is rho AV. Because we are focusing on the throat, so it is okay for us to write rho at throat, cross-section at throat, and velocity at throat. First, we could calculate the density at the throat by using this equation, P over RT. Cross-section area at throat can be calculated because the diameter of the throat is given, and velocity can be calculated because the Mach number is known, because we assume that Mach number here is equal to 1. So because we don't have any shock wave here, we could calculate P0, PT, and point at number 2 here by using the isentropic flow equation. So to get what is the pressure at throat, we could use the ratio for isentropic flow, P0 over PT, and this is the equation. We substitute the stagnation Mach number here is equal to 0, and Mach number for throat here is equal to 1. We substitute the value of K is 1.4 because our medium is an air. So we could get P0 over PT is equal to 1.89. So I hope you could have a very detailed number here. So and then we could calculate the pressure at throat by rearrange this equation, so it's become 102.54 divided by 1.89, and we could get the pressure at the throat is 54.17 kilopascal absolute. Then we need to calculate what is the temperature at throat. Again, we are using the isentropic flow equation for temperature ratio. We substitute all the value here, we could get that the ratio is 1.2. So we know that the temperature at stagnation condition means the temperature at the reservoir here is 25 degrees Celsius. We could convert it into Kelvin, and we could calculate to get temperature at throat here is equal to 248.3 Kelvin. And then we need to calculate what is the velocity at the throat. We know that the Mach number at the throat is equal to 1, and Mach number can be calculated by velocity divided by speed of sound here. So we substitute the value for Kr and T. So we found that the velocity is 315.9 meter per second. So we could calculate the rho at throat here is by using equation P over RT. We substitute the value of pressure, and then we times by 1000 because we calculate previously in unit kilopascal. We have the gas constant 287, and we have temperature for at the throat is 248.3 Kelvin. So we could calculate this one. We have density at throat is equal to 0.7602 kilogram per meter cube. Then we could calculate the mass flow rate, rho AV. We substitute all the value here and we could say that at the throat, the mass flow rate is 0.47159 kilogram per second. And the second question, he asked to, by maintaining the reservoir pressure, but reduce throat diameter to 40 millimeters, and we assume that Mach number at the throat is still equal to 1, determine the mass flux. So determine the mass flux. So we use the same equation. Mass flux is mass flow rate, so we calculate by using rho AV. We substitute all the value, but for this equation, for this solution, we need to use diameter of 0.04 meters because we change from 50 millimeters to 40 millimeters. We substitute in this equation, we solve it, we could say that the mass flux or mass flow rate at the throat of diameter 40 millimeters is equal to 0.30182 kilogram per second.